video is on sketching. You notice I have here sketching rational functions. You should be on page 775. The inverse variation equation, y equals a over x, which you learned in the last lesson, is a type of rational function. So not only were these called inverse variation, they're also known as rational functions. A rational function has a rule given by a fraction, you notice a fraction here, whose numerator and denominator are polynomials and whose denominator is not zero. We probably ought to review polynomials. Remember, polynomials can be monomials, binomials, or trinomials, or even more terms. What they're saying here, the numerator and denominator can be more than just a and x. It could be a polynomial like a binomial, a trinomial, and so on. We'll see examples of that here in a little bit. Denominator can never be zero, so you notice x can't be zero for this to be an inversely varying equation or a rational function. The parent rational function, you've seen this already. We've already had you graph some of these. The most basic function is y equals 1 over x. It's called the parent function. And again, you saw that in the video over 12.1. Now here's some key things about the parent function. The parent function and its sketch would have the following characteristics, two main things. The domain and range are all non-zero real numbers. Let's review why that would be the case. Why are they both non-zero real numbers? And I just drew it here in the picture. The parent function has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0, which means I can't plug in 0 for x and no value could ever equal y. So the domain and range are all non-zero numbers. They can't be 0. You can see the asymptotes are blocking out that the graph can't touch 0 for x or 0 for y. And I just kind of gave away the second aspect of the parent function. The horizontal asymptote is the x-axis. It's where y equals 0. And the vertical asymptote is on the y-axis. That's x equals 0. Let's talk about sketching rational functions. And turn ahead to page 777 because I want you to look at what I'm talking about here. You can sketch a rational function of the form y equals a over x minus h plus k by using the values a, k, and h. And real quick, this is very similar to vertex form quadratics. Remember, the vertex form, k and h gave you the vertex. Well, it's not exactly the same here, but here's what k and h and a will tell you. To sketch this, the sketch of this is a hyperbola that has the following characteristics. So when you sketch this thing, it's going to be the hyperbola, which has the two branches, and here are the characteristics. A, if a is greater than 1, the graph is a vertical stretch. If a is between 0 and 1, it's a shrink. And there's one more thing I should add to that, and you already learned this in the last lesson. If a is greater than I misspoke. If a is greater than 0, if a is a positive, if a is positive, the graph has to be up here in quadrant 1 and quadrant 3. So this would be an example of a sketch that's a is positive. If a is less than 0, which means a is negative, that means my graph is going to be in quadrant 2 and quadrant 4. Okay, so by looking at the a value, I can tell if this hyperbola is oriented, if a is positive, it'd be here and here, or if a is negative, it would be oriented here and down here. You've already learned that in the last lesson. Here's the second thing. The horizontal asymptote and the vertical asymptote are what the k and h tell us. So these two numbers will tell us where is the vertical and horizontal asymptote. H is the vertical asymptote. That's the one going up and down. And you got to be careful. You can see, let me erase some stuff here. The H has a minus in front, so whatever you see for H, it will be the opposite of what it looks like. And then the horizontal asymptote is whatever K is. Okay? I think the next thing to do is just actually do a few sketches. Let's try this one, and here are the directions. We're going to sketch this function and identify its domain and range, and we're going to compare it to the parent function. So here's the function, here's the parent function. First of all, here's my parent function. It has asymptotes at x equals 0, and it has an asymptote at y equals 0. Now, this function would be in quadrants 2 and 4 because a is negative. And you notice how I drew it farther away from the origin? It's because 4 is stretching the graph. Whenever the graph is stretched, it's farther away from the origin. Now I got to get some points. For the parent function, pick things that are easy to calculate. Like if I plug in 1, I get 1. If I plug in 2, 1 over 2 is a half. And if I plugged in a half, 1 divided by half is 2. Now you notice those points should be mirrored. So if I plug in negative half, I ought to get negative 2. If I plug in negative 1, I would get negative 1. And if I plugged in negative 2, I'd get negative half. And then I can do the same thing. I normally, when I have you sketch, maybe I should say this right now. When I have you sketch, I normally have you label 3 points on each branch of the hyperbola. Same thing here. If I plug in 1, negative 4 over 1 is negative 4. And if I plug in 2, negative 4 divided by 2 is negative 2. And if I plug in a half, negative 4 divided by half is negative 8. And then I can mirror those points. So if positive half gives me negative 8, negative half would give me positive 8. If 1 gives me negative 4, negative 1 would give me 4. And if 2 gives me negative 2, negative 2 would give me 2. It's very easy to mirror points when both asymptotes cross through the origin. If they don't cross through the origin both, then I'll have to show you some other things, but that's how you can mirror the points on a problem like this. Okay, what's the domain and range? The domain, it's all reals except x equals 0. Can you notice? X equals 0 has been blocked off. My graph can't touch x equals 0. And the range, you notice, this asymptote, we can never have a y value of 0. So my range is all the y values except for 0. Okay? And then I got to write 2 sentences comparing these things, and I put them on the bottom. I'm going to compare 2 things. How do they open, and where are the asymptotes? Both of these have the same asymptotes. They're both at x is 0 and y is 0. And y equals negative 4 over x is stretched because of the 4 and reflected because of the negative compared to the parent function. So you've done stuff like this. You've just done it for linear equations and linear functions. You've done stuff like this for exponential functions. And you've definitely done the same stuff for square root functions. Now, I'm just having you do it for rational functions. Okay? Let's try this one. Y equals 1 over x minus 4. Okay, so first of all, there's my parent function. It never changes. And you know the parent function, the asymptotes would be at x is 0 and y is 0. But now this function, the asymptotes, the horizontal asymptotes at negative 4. That's what this is telling me. So I'd have to go 4 units down and put an imaginary dotted line. My function will never cross over that. And then the vertical asymptote, I don't see any number in here, so I put x minus 0. So you notice there's no number in there. That means the vertical asymptote's at 0. That hasn't moved. Okay? This is going to look the same as the parent function. Here's why. Can you note they both have 1 over x. So I tried to draw these looking the same. I guess I didn't really do a great job down here. Let me maybe try redrawing it, make it look a little bit more that's better. Okay? So I want this to look the same, it's just 4 units down. Now, to get the points for these, it's similar. We have to pick some easy things, like if I plug in a half, 1 divided by half is 2, and 2 minus 4 is negative 2. And if I plug in 1, 1 over 1 is 1, minus 4 is negative 3. And if I plug in 2, a half minus 4 is negative 3 and a half. Now, I can't just do what I did before. You notice these asymptotes do not cross at the origin. The origin is up here. Let me highlight it. The origin is here. This is not the origin. So I can't just change the signs over like I did on the last one. But here's what you can do that might help you. Okay? Do you notice this point is 1 unit right and 1 unit above. It's 1 unit right and 1 unit above this asymptote. So this right here, these asymptotes meet at 0, negative 4 right now. Okay? This is y equals negative 4, and this is x equals 0. So these two asymptotes meet at 0, negative 4. So if this point is 1 right and 1 up, this point would be 1 left and 1 down. That's why I'm getting negative 1, negative 5. And if this point over here is 2 right, and it'd be a half unit up, this must be 2 left and a half unit down. That's why I have negative 2 and negative 4 and a half. And this point is 1 half right and 2 up. This would be 1 half right and 2 down. That's where I'm getting the negative half and the negative 6. So you can always get your points in that manner, or you can just plug them in and hand calculate it or calculate it in your head. Okay, I got to write 2 sentences, my domain and range now, and then explain how they compare. For this problem, the domain is all reals except for x. Right here, x can never be 0, so there's my domain, all reals except for x. And my range, my y values can never be negative 4, so there's my range, all reals except negative 4. And then my 2 sentences. This function is translated 4 units down from the parent function. That's why this horizontal asymptote is shifted. Or you could say it has a horizontal asymptote at negative 4 versus 0 for the parent function. That'd be another way of comparing the asymptotes. And then both branches of the hyperbola are the same because both hyperbolas had an a value equal to 1. One more to try. Describe how the graph of y equals 1 over x plus 3 is related to the graph of y equals 1 over x plus 3 is related to the graph of y equals 1 over x. Well, you notice these both have the same horizontal asymptote, because there's nothing being added here and there's nothing being added here. So my k value is the same at 0. My horizontal asymptote hasn't changed. What is different is that vertical asymptote. You notice this is telling me the vertical asymptote is moving 3 left here, where in this problem the vertical asymptote is at x equals 0. So this has a vertical asymptote of x equals negative 3, that's what this has, and this problem, or the parent function, has a vertical asymptote at 0. So that's how they would be related. They would look exactly the same, it's just this graph is going to be shifted 3 units left is what this is doing. Let's do one more sketch, and I think I'll be done with the video. Let's sketch. Now, this doesn't ask me to do domain and range and everything else. They just want me to sketch y equals 4 over x minus 5 plus 6. Okay, so first of all, my asymptotes. The plus 6 means my horizontal asymptote is 6 units up. And down here, this is telling me my vertical asymptote is 5 units to the right. Remember, where I'm highlighting, this is backwards from what it looks like. So this is positive 5. Okay, now here's the next thing. Do you notice how A is positive? That means my branches have to be in quadrants 1 and 3, which which are shifted up here and over here right now. The asymptotes are shifting my quadrants a little bit. So the sketch would look something like that. Okay, now let's get some points. Now, you don't want to just plug in anything, and I pre-made these points before I started playing the video. Here's why I'm picking these. I want something easy to calculate. Like if I put in 0, that's not great because I'll have 4 over negative 5, which is a decimal. I don't want to work with decimals. So let's plug in 6 because 6 minus 5 is 1. 4 over 1 is 4, and 4 plus 6 is 10. This must be 610. And then this point, 7. If I plug in 7, 7 minus 5 is 2. Well, that's easy. 4 over 2 is 2, and 2 plus 6 is 8. And then I pick 9 because that's easy too. 9 minus 5 is 4. 4 over 4 is 1, and 1 plus 6 is 7. Now, I can mirror these, but I've got to be careful. This is the point 5, 6. So do you notice, if this is 5, 6, this point is 1 unit over and 4 up. So this point would be 1 unit left and 4 down. So if I go 1 left of 5, that's 4. And if I go 4 down from 6, that's 2. This must have been 4, 2 here. It's got to be mirrored. Let me rewrite that 2. It doesn't look great. Okay. Now this point, if I go from 5, 6 to 7, 8, that's 2 right, 2 up. So this point must be 2 left, 2 down. Well, 2 left of 5 is 3, and 2 down from 6 is 4. This must be the point 3, 4. And then 9, 7, that would be 4 to the right and 1 up. So if I go 4 left of 5, that would be 1, and if I go 1 down, that would be 5. This must be the point 1, 5. So that's how I can get this sketch made, and I can get 3 points on each branch. The word problems, they're going to let you use your calculator for these. You can set up your equation, which you notice, this is a inversely varying equation. It's a rational function. And then they're having you put this in your graphing calculator and then using the trace key to approximate. So you've done that before. I'm not going to go through this more. I don't want to make the video longer than it is. If you do have questions about this process, make sure you ask in class. All right?